Hello everyone and welcome back to another minute concept, this time about predicting equilibrium with our reaction quotients. So like we determined in the last video, we can understand how the equilibrium constant is related to the amount of product and reactant based on, well, the value of the equilibrium constant. So we have, for example, the Kc, which is actually what we'll be dealing with primarily in this video. So when Kc is less than 1, if we recall, this means that the the reaction has more reactants or more reactants at equilibrium. Equilibrium. Now this could also be interpreted as reactant sided. There. Now, when Kc is greater than 1, more product at equilibrium. Right? Now, this is product sided. And when it's product sided, basically that just indicates that the forward reaction is more favored, and vice versa for and the opposite for when it's reactant sided, the backward reaction is more favored. Alright, so now enough with this recall. We also have when k is equal to 1. When k is equal to 1, sorry, let's recall this one too. When kc is equal to 1, equal portions. There. So let's just put this here on the side. And now let's understand what Q is. So there's QC and QP, but they have the same formula as their corresponding K. So in this video, we're going to be talking about QC. So QC is equal to the given concentration of reactants to their coefficient. Product to their coefficient over the concentration of reactants to the power of their coefficient. Now it's really just the same as how we compute for Kc. Now what's so different? QC, or just Q in general, the reaction quotient allows us to determine what will be produced more during the reaction in order to reach equilibrium. So we use QC when we're not yet at equilibrium, right? And how do we interpret whatever result we get here? Well, we interpret it based on whether or not we know what Kc is, right? So sometimes the problems that will be given to you will tell you that the equilibrium constant is, let's say, 1.2 times 10 to the power of negative 4. And at a certain point before equilibrium, it will give you its concentrations, the product and the reactant concentrations, and etc. And you want to know what the concentration of a certain product is at equilibrium, right? That's pretty much what it will look like. Now, I have an example of problems involving this here. Hold on. All right, so now let's consider this problem, right? So now we have the formation of nitrosyl chloride from nitric oxide and molecular chlorine. We're given the Kc, which is 6.5 times 10 to the power of 4, and we're given the moles of the reactants in the products. So what's the first thing that we have to do here? Well, the first thing that we have to do is write our QC expression, right? Now, how do we know that it's QC? As you can see, I already highlighted it here. When we see that the question is asking for where the system will proceed to reach equilibrium, that means we have to predict where it's going to go, where it's gonna shift, right? And proceed basically means shift. So we want to know where it's gonna go, and we use the reaction quotient to figure that out. Right, so let's draft our QC expression, or just our Q expression basically. And we'll see that we're going to have the NOCl on top, the power of 2. We'll have NO at the bottom to the power of 2 as well, multiplied by the concentration of Cl2, which is to the power of 1. Alright, now how do we get the concentrations from here? It's important to note that this is also using molarity. Alright, so QC also uses molar concentration, similarly to Kc. And we're given moles and volume. Now, how do we get molarity from here? Well, molarity is just equal to mole per volume, right? So now we can just go about our computation by using the given and using this formula. So for NO, the molar concentration of NO will be given by 2.0 times 10 to the power of negative 2, or 0.02 times divided by rather 2. Now the molar concentration of Cl2 rather would be 8.3, or 0.0083 over 2 liters. And for the bottom, we'll have, wait, don't forget the point 0 here, sorry, for significant figures. Point 0, point 0, and NOCl is going to be 6.8 over 2.0 as well. Alright, so now for here we'll get an answer 0.01 molar. This next one will get 0.00415 0.00415 molar, and for this one we'll get 3.4 molar. Alright, so now where do we go from here? Well, now we can just plug and play, right? So we have our concentrations. Now all we have to do is just compute, and I'll use a different pen here so that we can differentiate our solutions. On the top, we'll have the concentration of NOCl, which is now 3.4 molar to the power of 2, over 0.01 molar of nitric oxide to the power of 2, multiplied by 0.00415 molar. Sorry, my handwriting is going up a bit because of the space. Let me see if I can fix this. You know what? Let's just move all of this. There you go. Alright, so now simplifying this would actually get us an answer of an estimated amount of 2.8 times 10 to the power of 7. Now, what do we do with this answer? This is our QC now, right? This is our QC. We have to compare against our KC. And when we compare the KC, it's best to follow this format, the QC on the left and the KC on the right, so that we can have them as placeholders for reactants and products. That way, wherever the arrow is pointing, we know that that's where the reaction will shift, right? And so now let's write down our givens. Our reaction quotient is 2.8 times 10 to the power of 7. Our KC is 6.5 times 10 to the power of 4. And which one is greater here? Well, obviously, sorry, this is supposed to be a 7. Doesn't look like a 7. Let me erase that. Okay, there. 7. This is 4. Clearly, the left side is more favored, which means that the reactants are more favored, meaning it's a left shift. So it's a left-sided shift, or reactant shift. And that's how you use the reaction quotient in order to solve for the behavior of the system as it approaches equilibrium. Now, let's try and predict more things about equilibrium, right? And predicting equilibrium doesn't always mean that you have to use the reaction quotient, because there are a lot of things that we consider at equilibrium. There's concentration, there's the shift, which one will be greater in the equilibrium. Will it be the reactants or the products? Now, in some cases, we actually need to solve for the concentration of either a reactant or a product at equilibrium without us having their ratios, right? So we can't just use stoichiometry here. We have to figure out the concentrations at equilibrium before it even happens. Now, how do we do that? Well, allow me to demonstrate through a technique we call the ice table. Alright, so consider this reaction here. So we have water vapor reacting with carbon monoxide to turn into hydrogen gas and carbon dioxide. And this is a reversible reaction, so we have a Kc of 1.87. Now we need to calculate the number of moles of hydrogen gas formed at equilibrium if we have an initial amount, rather initial mole of carbon monoxide and water vapor in a 10-liter container. So we can't just use Kc here. We can't just use Kc like the product over reactant. We can't use Qc either because we don't have the amount of product at the beginning. And even if we did, it wouldn't get us anywhere, right? So what do we do here? We use the ice table. And I stands for, so let's put this here. I is initial, C is change, and E is equilibrium. Right? And this is our table. Oops, let me make that straight. Right, and then we're going to separate 4 columns there because we have 4 constituents here in this reaction. Now, what do we put in the first 2? Well, to figure that out, we have to understand first where is the reaction starting. So the first step in doing the ice technique is to just figure out the table, how to write the table, right? So we know that we're given the carbon monoxide and the water vapor, right? So that means where are we expecting the reaction to go? To the right or to the left? Since we're given reactants, we're expecting it to go to the right. So we put the reactants first. H2O and CO. And then on the right is our products, which we will use a yellow pen for. So we have H2, we have CO2. Now, the next step here is to write the initial concentration. Right? So all of these are all referring to concentrations. Okay. The ice table allows us to solve for concentrations at different points in the reaction, from a different point in the reaction to when it's at equilibrium. All right. So let's try and solve first for the initial. So our initial concentration, what's given to us are the moles of H2O and carbon monoxide. So is moles or concentration already? That's the first question, right? And the answer to that is no, because it's not in molar concentration just yet. So we have to convert that accordingly. And we can do so with this formula. So we have molar of CO. Well, and incidentally, the moles of H2O, since they're equal, right? They're both 0.300, will be equal to 0.300 over 10.0. And what is the answer to this? So that's basically just 0.3 divided by 10. Our answer here will be 0.03 molar. There. So that means our initial concentrations for H2O and CO would be 0.03 molar. Now, how about our initial concentrations of H2 and CO2? Well, obviously, nothing has been formed yet, so it will be 0. And it won't always be 0, because it will really depend on the question if they indicate that there's already H2 and CO2, but in this case, there isn't. Now, we don't know the change. We don't know the change that will happen to the reactants, other than the fact that we know that it's going to be decreased, right? And there's only 1 mole each. The ratio is 1 mole each in the reaction. So that means only one amount of change, or like an equivalent of 1 mole of change would occur to our reactants. So that means we have minus X change here. Now, of course, since we have to conserve mass, the law of conservation of mass, these two have to end up going to the other side, right? And it's not exactly -2 means that this side has to have +2. Instead, it's just whatever the moles again of these the right side products are, that's what we're going to have to put as well, because the change has to go somewhere. So since H2 only has 1 mole here, it has +X. Same thing with carbon dioxide. So that's our change. And just to clarify it, let's say that CO2 has a coefficient of 2, this would become 2x. Alright, so don't let that confuse you. Now, equilibrium is just the summation of this, right? So when we add all of this, at equilibrium, what do we expect? We expect to have a value of 0.03 minus x H2O, 0.03 minus x CO, and then we just have x and x for CO2 and H2. So basically what we did here is we're giving it an algebraic representation so that we actually can use these as our concentrations in our Kc expression, because these are now all concentrations, right? So let's go back to our Kc expression and let's write it with these as our data. So Kc would be equal to x times x, or okay, let's write it down first one by one. Let's write the whole expression first. CO2 over H2O and CO. And now if we simplify this, let's move this to the left. If we substitute our values here, we'll have these two are both equivalent to x, so that's x times x, which will just be x squared over 0.03 minus x times 0.03 minus x, which would just be 0.03 minus x squared. And what's our Kc? It's actually given to us. Our Kc is given as 1.87. So that means we can just substitute that here. Now, what's the next step here? We just need to solve for x, right? Because if we solve for x, that means we can figure out the concentrations of each of our constituents at equilibrium. So what do? We're just going to solve it using algebra. Now, when you see two expressions squared here, it's actually a lot easier if we just square root both sides, because this is essentially this is equivalent to x over 0.03 minus x quantity squared. So that also means we can give it a square root, so we can remove this side. So now we're going to be left with x over 0.03 minus x is equal to the square root of 1.87. Alright, so let's use a brighter pen here. Let's use yellow. So the square root of 1.87 is around 1.37. 1.37 is equal to x over 0.03 minus x. Now, where do we go here? We have to transpose, right? Not transpose, rather, we cross multiply so that we can isolate the x's. So that's 1.37 times 0.03 minus x. And this will be equal to x. Simplifying this side, we have to distribute 1.37. 1.37 times 0.03 is equal to 0.0411. So that's 0.0411 minus 1.37x is equal to x. Isolating the x's, we'll have x plus 1.37x, or just 2.37. 2.37x is equal to 0.0411, and we divide both sides by 2.37. This will leave us with an x of, hold on, an x of 0.0173, and there, that's our x. Now, I actually recorded a part of this already because I thought that the recording software was working, but it seemed to malfunction, so I now have a completed ice table here. So now let's just analyze it. So since we know that the change, or x here, is equal to 0.0173, we can calculate for our equilibrium concentrations by substituting x, right? And since H2O and CO are both equivalent, their equilibrium concentrations are going to be 0.0127, which we get from substituting x into the equilibrium here. And well, our change is also the amount of hydrogen gas, and carbon dioxide, which gives us 0.0173 m. Now what is this? Kc is greater than 1. That's how we interpret whether or not our answer could be correct or is likely to be correct, because since Kc is greater than 1, as we saw it was 1.87, we expect there to be more product at equilibrium, right? And we see that it's 0.0173 molar concentration of our products. And that's already a giveaway that we're on the right track because there's more products than reactants. And that is how you use the ice table. That is basically the process of predicting the concentrations at equilibrium. So before we end this video, let's give another example a shot so that we can just make sure that we completely understand how to use the ice table. Alright, so now let's try this question here. So again, we're given the reaction and we're asked to find the concentrations of everything at equilibrium. And since we're not at equilibrium yet, that means we have to find the equilibrium concentrations through the ice table. Now let's lay out our ice table. Alright, so the ice table begins with the I, C, E. And what's given to us first? The first thing given to us, I'll make this a bit lower. The first thing given to us is HBr. Now HBr is on the right side. So that means what direction are we going? So since we're on the right side, we're kind of tending to go towards the left. We have to go towards the left. So, hold on, let me actually zoom in a bit more so that we can make the lines a bit clearer. There you go. Alright, so using this, right, we have to make sure that HBr is on the left since that's what we're concerned with. So HBr is over here, and then we have two more columns, and this is going to be H2. Let's use a different pen here so that we can show that they're products, H2 and Br2. Alright, so now, what's our initial? Our initial concentration is not given in molar. So we have to solve for it first. So, based on the problem, we have to get the molar concentration of HBr, which is 3.20 divided by 12 liters. This is small. This will give us an answer of 3.2 divided by 12. 0.27, or for the sake of significant figures, 0.267 molar. So this is our initial, 267. Let's move this I down here so that it makes sense. We don't have any products yet, so this will be 0. Now our change will be equivalent to minus 2x rather, because we have 2 moles of HBr being consumed in the reverse reaction, and we'll have plus x and plus x on H2 and Br2 since they only have 1 mole each. So our equilibrium concentration would be equal to 0.267 minus 2x is equal to and then H2 rather would be x, and Br2 would also be x. Alright, so now let's move forward. What's the next step here? We have to identify our equilibrium expression. So our equilibrium expression, let's make this again bigger. Let's just write down the number before we zoom in. 2.18 times 10 to the power of 6. Alright, there. So I'm going to zoom in now. This is our Kc. So in the regular reaction, we would have it go towards the right. However, since it's reversed, right? Notice we're going from right to left. When we reverse a reaction, we actually invert our equilibrium constant. So this entire thing to the power of negative 1. We're getting the reciprocal of 2.18 times 10 to the power of 6. Because this time, our products are the previous reactants. So let's write this in red pen. This is H2 and Br2. And this is HBr power of 2. Alright, so moving forward here, we can further simplify. If we divide 2.18 2.18 times 10 to the power of 6, and then now we make this to the power of negative 1. We'll get an answer of 4.59 to the power of 4.59 times 10 to the power of negative 7 is equal to x squared, since these two are both x, over 0.267 minus 2x squared. Now, same thing. Since they're both squared, we can get the square root of each side. So now we'll go with, let's use the purple pen. So we'll get the square root of both sides. And we'll be left with, let me get the square root of 4.4 and the power of square root of this is approximately 6.77. 6.77 times 10 to the power of negative 4. And this will be equal to x over 0.267 minus 2x. Alright, and now we're going to further simplify. And just to save us time here, let's see if you guys get the same answer. We would arrive with an x of 1.81 times 10 to the power of negative 4. So let me write that down here. 10 to the power of negative 4. Alright, so now we want to get the concentration of everything. So we're just going to copy paste this and put this back up here. We know that this is now also incidentally the concentration of H2 and H2 and Br2. And we just have to solve for HBr now. So we can solve for that with our calculator. So 0.267 minus 2 times 1.81 times 10 to the power of negative 4. And that's going to give us an answer of 2.67 times 10 to the power of negative 1 is equal to the concentration of HBr. Our Kc here, Kc is, hold on, our Kc is, let's not use this one, let's use a different one. Let's just use this one. Kc is less than 1, so that means there should be more reactant favored. Now we just compare these two. Which one is more, the reactant or the product? Well, as we can see here, our reactant is more. This is greater than, let's just invert it there. So it's greater than the amount of product, which means that our answer is correct. So that's it, and that's how you use the ice table and reaction quotient to predict the behavior of a certain reaction or set of reactions at equilibrium. Hold on, where do we start? Right here. So thank you everyone, and I hope you learned something. This video is a bit long, but it's really worth practicing because this is a very important technique that you will use not just for equilibrium but also for a lot of different related topics, as ice table really it reappears very often. So thank you everyone, and I hope you learned something once again. And if you have any questions, please just comment down below, and I hope you learned something. Bye bye.